Alright, welcome to the first part of our unit number 6 on work and energy. So today we're going to talk about work. And as you can see here, work is done when an object moves. This is a simple way of thinking about it, but typically if you're moving somehow at some point, there's work done. It's more elaborate than that, and that's where the actual definition involves more ideas than just moving. So the work is the product of the force and the distance the object moves. And the key here, though, is that the direction of the force and the distance need to be parallel, which means they can be in either the same direction or the complete opposite. But if they're perpendicular, you actually end up with no work done. So they have to be in the same direction. So we get our equation, work equals force times distance. In future studies of physics, there will be an additional trig part on there, but we won't worry about that this year. You'll see that in the future. So you have units of force times distance, which is a Newton times meter. So we'll work with Newton meters, which is fine. We're later going to see that that unit is equivalent to a joule. So let's take a look at a couple of examples here. So we got a 105 gram hockey puck sliding across the ice. The player exerts a force of 4.50 newtons on the puck over a distance of 1.50 meters. How much work does the player do on the puck? So you'll notice with work questions, it's always about a specific force. So this time we're looking for that force applied, which we're given. Always make sure that you're in kilograms. So we need to make this 0.105 kilograms. And then, well, we just go into our formula, force times distance, and we're given the force 4.50 newtons times 1.50 meters. And that's going to give us, with 3 sig figs, 6.75 Newton meters or joules, but that's our answer. As simple as that, just plug and play into the equation. We did not actually need the mass in this question. So let's take a look at the next one. A student lifts an 18.5 kilogram box of books. If the student lifts the box of books 0.800 meters, how much work does the student do on the box? So again, we got our mass in kilograms, our distance in meters as we need, and we want to get the work. So we go to our equation, work equals force times distance. Well, the problem is we don't have an actual force in this question, so we need to figure out where the force comes in. One thing you got to remember from the forces unit is the word lifts implies something about the F net, which is that it is equal to 0. So if we think about drawing a free body diagram, we've got an FG going down and FA that is lifting the books up. And we know that if F net is equal to 0 newtons, then that means FA has to equal FG. And we know FG is equal to mg, so we end up with FA is equal to mg. Well, now we are at our force, so let's put in the force as mg times our distance. Now we have m, we know g and d, so we can plug everything in now. 18.5 kilograms, 9.80 meters per second squared, and 0.800 meters. And our work is going to be 145 Newton meters. So, as I said before, it's always the work done by a specific force. So in those two examples, it was an applied force, one by the player onto a puck, and the other on lifting up a box. So the way we can think about this is if we have a situation of a box being pushed across the floor at a steady speed. Steady speed implies that the net force is 0. So we can relate all of our forces together using that sense. So we have our free body diagram with our applied force, friction force opposing it, Fn and Fg. So if we're thinking about just positive, negative, or 0 for the work done by Fa, Fa is in our positive direction of our moving velocity, So that will be positive as well, which makes sense. Everything's going in the same direction. Friction is going in the opposite direction. So it's still parallel, but it is opposite to the direction that we're moving. So the force would be like a negative, which would mean that our work would be negative as well. Now, if we're thinking about Fn and Fg are both perpendicular to our distance that we moved. And if we go back to our definition, they have to be parallel. When they're perpendicular, you're actually going to end up with zero work. So in both of those situations, because the normal force and gravity are applied in directions that are perpendicular to the direction that the box is moving, the work done is zero. We can do one more, and if we wanted to think about Fnet, which we rarely do when we're talking about net work, but the net force would be related to the net work done. And in this case, we know the net force has to be zero, and if work is force times distance, if the net force is zero, then the overall work done also has to be zero. And we can think about it as adding up the work done by the applied force and the work done by friction. If the two forces are the same, but just opposite directions, and the distance is the same, then those two are going to cancel out, so we end up with zero. So that's a little bit about work, and as always, physics is awesome.